We're going to calculate the colligative properties of a particular solution of 2,315 grams of sucrose in 4,029 grams of water at 25 degrees Celsius. The density of this solution is 1.029 grams per milliliter. We're going to need the density when we get to calculate some of these values. We're going to calculate the freezing point depression, the boiling point elevation, the vapor pressure, and the osmotic pressure. Now, I looked up ahead of time some constants that we're going to need to calculate all of these, and these will always be available in a table or they'll be given to you. They're not something that you would calculate, although you could determine these experimentally. And we have things like the vapor pressure. Pure water at 25 degrees Celsius is 23.76 torr. The normal boiling point is 100 degrees Celsius. And the boiling point elevation constant is 0.51 degrees Celsius per mol. The normal freezing point is 0 degrees Celsius for pure water, and its freezing point depression is 1.86 degrees Celsius per mol. And we'll also need the gas law constant, and the one that we're going to use today is 0.08206 liters atmospheres per mole Kelvin. Now we're going to calculate 4 colligative properties, and we can do any of the 4 in any order that we want to, and I'm just going to start with freezing point depression. Now freezing point depression is given by this relationship. We got K F for freezing times the molality, and the molality is moles of the solute per kilogram of the solvent. The solute today is sucrose, and the solvent is water. Now we're going to need to find the moles of the solute first, which is sucrose, and to find the moles we're going to need the molecular weight of sucrose, and sucrose is C12H22O11, and we can calculate that out, and it is 12 times 12 plus 22 times 1 plus 11 times 16. These are the individual atomic masses of the various atoms, and we go ahead and multiply that out. We get 342 grams per mole for our sucrose. Now we were given that we have 2,315 grams of sucrose, and we're going to need moles on top and grams on the bottom to cancel, so we go moles per 342 grams, and we go ahead and put that in our calculator, and we get 6.769 moles of sucrose. So almost there. We're almost there as far as calculating the molality. And the molality, put it all together, is going to be the moles we just found divided by the mass of the water, which is 4.029 kilograms, recalling that we started out with 4,029 grams, and that's 1 kilogram per 1,000 grams, which equals 4.029 kilograms. That's where we got the kilograms from. And we divide that out, pull out our calculator, and we get 1.68 molality in sucrose in water. And now we're almost done. And so our delta T for freezing is equal to our KF, which we've already looked up, and it is 1.86 degrees Celsius per mol times the molality that we have found, and we get 3.12 degrees Celsius. And so our new freezing point is our pure water freezing point minus our freezing point depression, which is minus 3.12 degrees Celsius. There it is. Now our boiling point elevation is a very similar calculation, except we have a new constant, and it's K sub B for boiling point elevation. And our boiling point elevation was given to us originally. There it is, 0.51 degrees Celsius per molal. And it looks just like this. Delta T for boiling point elevation is our K sub B times our molality. And we've already calculated our molality. We did that right here, where we calculate the molality for the sucrose. Now it was 1.680 molality in sucrose. So all we got to do is just plug it back in. So delta T for boiling point elevation is going to be 0.51 degrees Celsius per molal. We looked that up, remember? And that is times our molality, which we already calculated. And that is 0.86 degrees Celsius. And so therefore our new boiling point is 100.0 degrees Celsius plus 0.86 degrees Celsius, which is 100.86 degrees Celsius. And there's our boiling point elevation, and there's our new boiling point of our water with sucrose mixed in. Next, let's calculate the vapor pressure of this solution of sucrose in water. Now the vapor pressure of the solution is different from the previous ones we calculated. The vapor pressure of the solution is equal to the mole fraction of the solvent times the pressure of the pure solvent. Now this is different from the other colligative properties. We have to be careful that we're using the pressures of the solvent and the mole fraction of the solvent to calculate the pressure of the solution. First off, we have to calculate the mole fraction, and the mole fraction is the moles of solvent divided by the moles of all the solutes plus the moles of solvent. Okay? Now the moles of the solvent we need to calculate, and it's water, and we have 4,029 grams of H2O. That's the mass of the water. And the molecular weight of water is 18.0 grams per mole, so we multiply times moles over 18.0 grams per mole of water. And we get for this mass of water is 223.8 moles of water, H2O. Now our moles of sucrose we've already calculated, but we'll go ahead and do it anyway, and it's 2315 grams sucrose, and a mole of sucrose is 342 grams, and that gives me 6.769 moles of sucrose. And so we just need to add them all up and divide, and we've got 223.8 moles of water divided by the moles of water plus the moles of sucrose, and that gives us a mole fraction of the solvent, which is the water, of 0.9706. And so the new pressure of our solution is going to be that mole fraction times the vapor pressure of the water at 25 degrees Celsius, which we've already looked up, and that's 23.76 torr. And that gives us a new pressure of 23.06 torr. And of course, just a reminder, we looked that up first. Finally, we're going to calculate the osmotic pressure of this solution of sucrose in water. And the formula that we need for osmotic pressure is given by pi equals the molarity times the gas law constant times the temperature in Kelvin. Now this is different from lowercase m because molarity, big M, is moles per liter of solution. So we're going to need to find our moles, we already have, of our sugar, and then we're going to have to figure out how many liters total we have of the solution, which was not given to us. But we can calculate that because we have the density of the solution. So first off, let's just get our moles of sucrose. And that's equal to 2,315 grams times moles per gram. It's 342 grams per mole for sucrose. That's molecular weight. And we multiply that out, and we get 6.769 moles of sucrose. Okay, so now we have the moles part. Now we need the liters of solution. Well, to get the liters of solution, we need density. And the mass. Okay. And our total mass is going to be the mass of the sugar, which is 2315 grams sucrose, plus the mass of the water, which was 4,029 grams, which is going to be equal to 6,344 grams total. Now we're almost there to our liters of solution. We have the density, which was already given to us, so our volume is the mass of our entire solution, which was the grams of the sugar plus the grams of the water, times the density, which was 1.029 grams per milliliter, so we'll put milliliters on top, which is 1.029 grams. That was the density of the water solution. And remember, we want this in liters, and this is milliliters, so we need to go ahead and take our milliliters to liters, and it's 1,000 milliliters equals a liter. We see that milliliters cancel, grams cancel, so we're left with liters, and that gives us, put it in our calculator, we get 6.165 liters of solution. So we have our moles, we have our liters of solution, so we can calculate our molarity of our solution, and that is 6.769 moles per 6.165 liters, which gives us a molarity of 1.098 big M, molarity, moles per liter. And finally, we can plug everything in here, and so our osmotic pressure is the molarity, which we just calculated, 1.98 molarity. Our R, well, we'll calculate our pressure in atmospheres, so we're going to use 0.08206 liters atmospheres moles Kelvin. So we get our answer in atmospheres. And finally, by our temperature, and our temperature is 25 degrees Celsius, so that's 298 Kelvin. And that gives us a final answer of 26.9 atmospheres. And there you go. That's the osmotic pressure of a solution of sucrose and water.